Let's wrap up what you have done until now. If I take this notation, which contains the time complexity pre-processing, the time complexity of a single query, and the extra space complexity. We have seen that the naive approach is constant time for pre-processing, linear time for a single query, and constant extra space. The prefix sum, which works only for the static range sum queries. It's linear time for pre-processing, constant time for single query, and linear extra space. The dynamic programming approach we used here a matrix that computes all the ranges in quadratic time pre-processing, constant time for single query, and quadratic extra space. And also we have seen the square root decomposition, which takes linear time for pre-processing, square root of n for a single query, and big O square root of n extra space. In this part, we will see another technique which called the sparse table. What's the idea behind this technique, or what's the intuition here for this technique? We know that every positive integer can be uniquely represented by the sum of powers of 2. If we take this example, 21, it could be written using this sum, 1, which is 2 power 0, 4, which is 2 exponent 2, plus 16, which is 2 power 4. It's the sum of powers of 2. We know that using this binary representation of the integer 24. So every natural integer, the greatest power of 2 included in the sum of powers of 2, of course, of x is equal to 2 power the floor of log base 2 of x. How we found this? If we take x is a power of 2, let's call it k, 2 power k, we can compute this k, which is the greatest power of 2 and the sum, which is equal natural logarithm of x is equal 2k times the natural logarithm of 2. So k is equal natural logarithm of x over the natural logarithm of 2, which is log base 2 of x. It could be a real here. We will take the floor of this mathematical expression. Let's take an example here for 21. 21, as you see, the greatest power of 2 included in the sum of power of 2s of 21 is 2 power the floor of log base 2 of 21, which is 4. This value is 4. So 2 power 4 is 16, which is this one. Consequence of this intuition, instead of building a matrix of size n times n, as we have seen in the dynamic approach for static queries, we can build or construct a matrix, let's call it ST, of size n times log base 2 of n the floor plus 1, such that Stij store the function f, min or max or the sum of the next 2 power j elements starting from I, which means Stij is equal f function f we apply the function f on the original array from I to a position p. What's this position p? Let's see now. Let's see this definition represented by this schema. Let's take from I, we're going to take 2 power g elements. This minimum here, this minimum or max or the result of f is represented here in the sparse table of this matrix. As we have said in the beginning, that this matrix is of size n times log base 2 of n of the floor plus 1. So this value here in this red cell here is the result of f in the initial array from I to p. So from I we take the next 2j elements and we apply f and this on these elements here. But what's this position p? We know that from I to p there are p minus I plus 1 elements, which is equal 2 power j. The number of elements here is 2 power j. So we can conclude that p is equal to I plus 2 power j minus 1. So, and the value st of ij, which is this value, the value here in this in the matrix, and the column and the row I and the column j, which is 2 power j, is equal to the result of the function f from I to this position p, which is this value I plus 2 power j minus 1 in the original array A. This is the idea behind the sparse table, where we have to be careful here that 2 power j, the number of elements, must be at least 1 element and at most n elements. It could be here the total number of elements in the array, which is the number of elements that we're gonna to take. And this position p, which is this value, must be, of course, between 0 and n minus 1 inclusive. So I plus 2 power j minus 1 It could be greater or equal to 0, but less than n, which is 0, less or equal to n minus than n minus 1. I repeat here. We're going to take 2j elements in the original array. We're going to take 2 power j elements from position I to a position p, which is equal to this value. Because the number of value here in this range is p minus I plus 1, which is equal to 2j, 2 power j elements. So we have p is equal to I plus 2 power j minus 1. So this value on the cell, in the matrix here, in the column, on the row, sorry, I, and the column j, stij is equal to f from I to I plus 2 power j minus 1 in the original array. Let's take an example here, or let's see how to build this sparse tape. Let's take an example, and from that, and at the same time, we're going to see the naive approach how to build this array. Let's take this array of 10 elements. So the size of the sparse table is 10 times log base 2 of 10 plus 1, which is 10 times 4. We have the rows represented by the pointer I, and the column represented by the pointer j. So we have from 0 to 9 here, which is the n elements, and this is here. And on the columns, we have 4 columns here, which is column 0, that represent 2 power 0. And the column 1 that represent 2 power 1, column 2 represent 2 power 2, and column 3 that represent 2 power 3. How to build this cell, the green one, which is ST00, row 0, column 0, which is the minimum, or F. Let's take the minimum here. F is min. The minimum of the next 2 power 0 cell, which is 1, starting from 0, which is this one. So what's the minimum of 6? Is 6. ST10, which is this one. Let's fill first the first column. ST10. This represents the minimum of the next 2 power 0 cell, which is 1, starting from 1, not 0 here, sorry. Starting from 1, which is 9. Let's continue for this. So here in the ST20 means the minimum of the next 2 power 0 cell, because we fill, why 2 power 0 here? Because we are filling the column 0, this one. This is the starting indexed in the original array. So from index 2, we're going to take one cell, which is the minimum here, which is this one, 2. Same here. from 3, we're going to take one cell, and the minimum of this value here is 4. Same for 7, 8, 5, 8, 3, 7. So we take here every one cell. So from I on the column 0, from I, which is I from 0 to 9, we're going to take just one cell, 2 power 0, one cell, and compute the minimum. As you see here, is nothing is nothing but the original array, the values of the original array. Let's go to ST01, which is this one. What does mean? It means that we're going to take the minimum of the next 2 power 1 cells, which means 2 cells starting from 0. We're talking about these 2 cells. So we're going to compute the minimum of 6 and 9. So 6. Let's see. ST11, it's the minimum of the next 2 power 1 cells starting from 1. These 2 cells. So the minimum between 9 and 2. So 2. And so on for the other. Let's take, so another last example here in the second column. What's the value here? ST71, which means the minimum starting from 7, we're going to take 2 power 1 cells, which means 2 cells, these 2 cells. So the minimum there is 3. And we'll continue all the last one here. In 9, we cannot take 2 cells here because there are no 2 cells here, so we do nothing. Let's go to the third column. ST02, which is this one, the blue one, blue cell. So we're going to take the minimum starting from 0 of the next 2 power 2 cells, which is 4. Minimum of the next 2 power 2, which is 4 cells, starting from 0. We speak about these 4 cells. So the minimum here, as you see, is 2. It's 1. Same if we start from 1. ST12 is the minimum, this cell is the minimum of the next 2 power 2 cells, which is 4, starting from 1 this time. So the minimum is 2. And so on for the other cells. So here we stop at index 6 because from 7 we cannot take 4 sets. Let's fill the last column. S03 is the minimum of the next 2 power 3 cells, which is 8 cells, starting from 0. We speak about this 8 cells. 2 power 3 is equal to 8. So the minimum there is 2. And ST13 is the minimum of the next 2 power 3 cells, starting from 1, which is this cells, from 1 to 8, the minimum is this 2. And ST23, we're going to take the minimum of the next 8 cells, starting from 2, this time, which is 2. And we stop filling here because from index 3 and 4 and 5, we cannot take 8 cells. So we stop filling the table here. This is how to build the sparse table, the concept or the idea of building the sparse table. But this approach is naive because to build the sparse table, we have to fill all the matrix which takes n log n time complexity, and for every cell we're going to run or iterate over the number of cells. It could be, in the worst case, it could be n, so the whole time complexity is big O n squared log n, which is very bad. Of course, we can build this sparse table efficiently. How we can do this? We know that 2 power j is equal to 2 power j minus 1 plus 2 power j minus 1. How this is true? We know that 2 power j is equal to 2 times 2 times 2 times and times until 2. This we can take this g minus 1 times. So times 2 to complete the j. This is 2 power j. This is j times, and this is j minus 1 times. So as you see here, we can write that 2 power j is equal to 2 times 2 power j minus 1, which is 2 power j minus 1 plus 2 power j minus 1. So this way. This is lead us that St of I j, the purple cell here, is equal these two cells starting from I to P, where P is I plus 2 power j minus 1, as we have seen in the previous slides. So we're going to take 2 power j cells from I to P, which is St ij, which is equal to, we can use this two values here to compute the f, or the minimum here, if f is equal to min. The first one here, and the green one, is Stij minus 1, which is the number of cells from I to in any position. We don't know, we don't care about the position here, but what we care here is the number of cells from I. We're going to take 2 power j minus 1 cells, and the other, this, which is the green one here, the green cell here in the matrix, and the other value is St, unknown position, to j of j minus 1. Why j minus 1? Because we have here 2j minus 1. So this one refers to this, and this one refers to this. We know that the column is j minus 1 because the power here is 1. But we don't know the row. How to compute this row? If we do here, we have 2 power j minus 1 sets for this. So this for this, and the green one, the number is for this. Okay. What about the row now? The row, we can compute it easily by using if let's say k, the end of the green part, the first 2 power j minus cells, so the next one is at start from k plus 1. If these cells end at position k, so the next 2 power j minus 1 cells start from k plus 1. It makes sense. So we can compute. We know that from I to k, we have 2 power j minus 1 cells, and also we have k minus I plus 1 cells. It's the same value. The number of cells in this range here, is k minus I plus 1, which is 2 power j minus 1 cells. So k plus 1 is equal to I plus 2 power j minus 1. We can use this formula as we can use this one. It leads to the same result here. So the row here, if we want to compute Stij, we can use these 2 cells, Stij minus 1 and St, the row now, I plus 2 power j minus 1, this is the row, and the same column j minus 1. This formula came from this one, and from this one we can explain this formula using this schema here, and we can compute the row of the next cell. So we can use here a dynamic programming approach known the tabulation, or as known as the button up technique. Let's take an example here. If we have this array and we want to build efficiently the sparse table, first we're going to fill the column by the elements of the original array A. First column by the original array. And we can use that information, which is the first column, to calculate the next one. We know that Stij is the minimum between Stij minus 1 or St, the value on the sparse table at the row I plus j minus 1, column j minus 1. If you want to compute St01 is the minimum, which, as we have seen, then the next 2 power 1 cells, which is 2, starting from 0. So we can use this the formula. 2 power 1 is 2 power 0 plus 2 power 0, as we have seen in the previous slide. 2 power 0 is the minimum of the next 1 cell starting from 0, which is this one in the sparse table, the red one here. And 2 power 0 is the minimum of the next 1 cell starting from 1, which is this one in the sparse table, which is St10. So that leads us that St01 is the minimum of St00 and St10, which is here 6. If we want to compute ST1 now, what's the minimum of the next 2 power 1 cells started from 1 here, sorry, from 1, not from 0. So 2 power 1 is 2 power 0 plus 2 power 0, and 2 power 0 is the minimum of the next one cell started from 1, and 2 power 0 is the minimum of the next, of the red one, of the next one cell started from 2, as you see, which is the minimum between 9 and 2, which is 2. And we'll continue like this for the next value of the second column. This purple, this value here, which is the minimum between 2 and 4, these 2 ones. And this is 2. And this is 2, which is 7, and so on, until filling the entire column. Let's make the same thing for the third column, the column number 2, or 2 power 2 if you want. S02 is the minimum of the next 2 power 2 cells started from 0, as we have seen. We can write 2 power 2, which is 2 power 1 plus 2 power 1. The first one, the red one, is the minimum of the next 2 cells started from 0. And the green one is the 2 power 1 from the next 2 cells starting from 1, not from 2, yes, from 2. We can compute this also using this formula, which is ST02 is equal to ST01, and the minimum between ST01, which is the red one here, this one, and ST of 0 plus 2 power j minus 1, j is 2 here, which is 1, which is 2 here. We have 0 plus 2 power 1, which is 2. 2 and j minus 1 is 2. So, j minus 1 is 1, sorry. 1 here. So, ST02 is equal the minimum between ST01 and ST21. This one, ST21, which is 2. Let's take another one. We're going to compute this value. We can use this formula, which have been calculated in previous slide. ST0 is ST12. ST12 is equal to ST1, 1, j is equal to 2 here, and ST21 plus 1 plus 2 power 1 is equal to 3. 3, 1. So the minimum between ST11 and ST31, as we have seen here in the picture. Okay. The same, this logic leads us as the same result here, which is 2, the minimum. And we can continue for other cells on the third column. This one is the minimum between 2 and 7. This one is the minimum between 4 and 5. This one is the minimum between 7 and 5, which is 5. And this one is the minimum between 5 and 3, which is 3. And this one is V2. Let's fill the same, let's do the same for the last column. We can use this logic. ST03 is the minimum of the next 2 power 3, which is 8 cells starting from 0, as 0 is 3, started from 0 here. We can use this formula to use the previous column, or this one. So 2 power 2 is the minimum of the next 4 cells starting from 0, which is this value, which is 2 power 2 here, this value, this is 2. And 2 power 2 is the next of the 4 cells starting from 4, this one, this one. So this cell is the minimum between 2 and 5. Let's try using this formula. ST03 is equal to minimum to 0, 2, and 0 plus 2 power 2 is 4, 4, 2, 4, 2. Okay, this is the same result as you see. So ST03 is the minimum between ST02 and ST42, which is the minimum between 2 and 5, which is 2. Same logic for the other cells. Here, ST13 is the minimum between ST12 and ST52, which is 2 and 3, which is equal to 2. And the last value in the last column, ST23 is equal to ST22 and ST62, which is 2 and 3. The minimum between 2 and 3 is 2. Let's see the pseudocode of the function build. It's the function that will build the sparse table. It takes as parameter, we can take as parameter the original array A and the number of element n, or the size of A, the original array. First, we compute the size of the sparse table using this formula, as we have seen in the previous slides. The size of the sparse table, and we're going to fill the first column with this loop, for loop, for I from 0 to n minus 1 inclusive st of I0 is equal to ai, and for j is equal to 1, we're going to fill the next columns now from 2 to n if you want. Iterate over the columns, then iterate over the rows, and as you have seen previously, that we're going to take every time 2 power j elements, so at least we have 1 element, and at most we have n elements. So here, same for the position of the, if we take from I, we take 2j elements, we end at the position I plus 2 power j minus 1. If you forget this, guys, you can come back to the previous slides and see how we can find this value. So the position here, it must not exceed the indices of the array, original array. So we're going to put here 2 power j, and on the next loop I plus 2 power j minus 1. And using dynamic programming, as we have seen, every time we're going to use the previous column to compute the minimum of the value of the current column. So we're going to compute stij using the previous column, using dynamic programming with the bottom-up approach or technique. We know that the size of the sparse table is n times log 2n plus 1. So to fill this table, it costs n log base 2n in time, and n log base 2n space. How to query now? How to query using this sparse table. If we want to query for example, the range minimum query on A from A to D, but we know already we know the minimum on A from A to B, and the minimum on A from C to D. And as you see, the two ranges overlaps here. The two ranges overlap. We want to know the range minimum query on A from A to D. And if we already know the range minimum query from A to B and from C to D, A and B, C and D overlap. There is no problem on the minimum here because we will take the minimum of all the range. We can combine the two ranges to compute the minimum. Can we do the same for f if f is the sum or the product, for example? The answer here is no. No, because we're going to count the same elements twice because we overlap. So here, before that, we have to make sure that the function f that we were going to compute is idempotent binary operator. Mathematically, which means f of x is equal to x. For example, here, we know that the minimum is of 3. 3 is equal to 3. Max 3 of 3 is equal to 3. JCD, great common divider, of 4. 4 is equal to 4. But, for example, the sum of 3 is not equal to 3, is 6. So we cannot use the sum using the sparse table. The example of idempotent f's are min, max, JCD, boolean and boolean or bitwise and bitwise or etc. We can you can see that in the Wikipedia to go deeply what's the meaning of idempotence or an idempotent function. So let's query how to query from left to right in the initial array using the sparse table. First, we compute the number of elements. As we have seen, all the idea of the sparse table is taken a power of two elements, two power g elements in that range. So first we compute the number of elements in that range. Let's call it len, which is right minus left plus 1, r minus l plus 1. And compute k, which is the greatest power of 2 in len, as we have seen in the first slide or the second slide, which is the floor of log base 2 of the length of that range. So we can say that STLK, which k is not this k, there is a mistake here, sorry, mistake is not in the equation here, we can this k. So STLK is equal to the range minimum query on A from left, as we have seen, to the position left plus 2 power k minus 1, which is the green one here, the green cell. This is L. From L to we have taken 2 power k cells, as you have seen the green one. What about the rest now? The rest of the range. We're going to look for a position P such that the number of cells from P to R is 2 power k cells 2. It could be from this position in the table. It could be from there. So we can compute this P, because we know that the number of cells from P to R is equal to R minus P plus 1. Plus 1, not minus 1 here. So here we have minus 1. So let's repeat this. We're going to look for a position P such that the number of cells from P to R is 2 power k cells. We know that the number of cells in range R, P to R is R minus P plus 1 is equal to 2 power k. So P is equal to R minus 1 minus 2 power k. Yes, plus 1 here. Sorry for this, guys. So here, using this formula, we can use this one. We can compute P. P is equal to R plus 1 minus 2k. So SPK is the minimum from P to P plus 2 power k minus 1, which is the position starting from P if we take 2 power k elements. So the green one here. So we have found our position P. The idea here is to find in this range is to find 2 ranges that have 2 power k elements, which is k is the greatest power of 2 of the length of that range. And if we have these 2 power k elements, we can use the sparse table to compute that minimum. So the minimum of the range left to right is equal to the minimum on the sparse table of the cell and at the row L column K and the row P column K. Let's take an example here. If I want to query on A from range 3 to 5, compute the length of that range. 5 minus 3 plus 1 is equal to 3. Compute k. K is log base 2 of 3 is equal to the floor of log base 2 of 3 is equal to 1. So the first value is the starting from 3. Look at the next 2 power 1 cells, which is 2 elements, which is 2, 1, which is that value is stored in the sparse table at position 3, 1, which is this one, the red one. And we can compute P now. P, as we have seen in the formula, it's the position that start the next 2 power 1 elements. So from 4, P is 5 plus 1 minus 2 power 1, which is 2 is equal to 4 here. So starting from 4, look at the next 2 power 1 elements, which is 2 elements. So it is stored at the column 4, row 4, column 1 in the sparse table. So the minimum on the range 3, 4, 3, 5 on the original array is the minimum from 3 to 4 combined to the minimum from 4 to 5, which is the range 3, 4, 3, 5 as you see. So 3, 5, we divided 3, 5 to 2 ranges, to 2 sub-ranges if we can say that. 3, 5 from 3, 4 and 4, 5. So which is the minimum in the sparse table now at ST31 and the minimum between ST31 and ST41, which is the minimum from 4 at 7, which is 4. Sorry for this, guys. I don't know what happened here. Okay, which is 4. As you see in the original array, the result is correct. The minimum in the range of from 3 to 5 is 4. Okay, let's take another example. The minimum from 3 to 7 in the original array using the sparse table. So we're going to compute the number of cells in that range, which is 5. 7 minus 3 plus 1. We're going also to compute the power, the greatest power of 2, and that contain 5. That could contain 5, which is 2. 2 power 2 is 4, as we have seen in the first slide. That k is the greatest power of 2 included in the sum of power of 2's of 5, because 5, it could be written 2 power 0, which is 1, plus 2 power 2, which is 4. So we have found the power here, 2. 2 power 2 is 4. So it means starting from 3, we're going to take 2 power 2 elements, which is 4. So from 3 to 6. What about the rest now? We're going to compute or to look for another range of 2 power 2 elements that ends at 7. So we have to compute the position, the starting position, the beginning position. This is the S232. So the position E is 7 plus 1 minus 2 power 2 is equal to 4. We have seen how to compute this position in a previous slide. So starting from 4, look at the next 2 power 2 elements, which is ST42, this one. So the minimum from 3 to 7 in the original array is the minimum from 3 to 6 in the original array combined to the minimum of from 4 to 7. There is no matter that the ranges overlap here because the minimum is the idempotent function. So the minimum is of between 4 and 5 is 4. As we have seen here in the initial array, from 3 to 7 is the minimum is 4. One last example. The minimum from 0 to 7. Compute the length, number of cells equal to 8. The greatest power. Now we're going to compute the greatest power included in the sum of the power of source of 8, which is 3, because we can 8 is 2 power 3. So it means starting from 0, which is the left boundary here, starting from 0, we're going to look at the 2 power 3 elements, these 8 elements, which is ST03, which is this one in the sparse table, the red rectangle here. And we have to find the position that start from that position. We have to take 2 power 3 elements and end at position 7. So from P to 7 we must have 2 power 3 elements. We can compute it using this formula. 7 plus 1 minus 2 minus power 3 is equal to 0, which is this formula. No, here I think, no, here, no, here. Okay, this one. We have explained how to compute that position here. Okay, let's come back to the example. So we have found the first range. The second range started from 0. So starting from 0, look at the next 2 power 3 elements, which is the same range here, ST03. So the minimum between these two ranges is 2. The range query here, so it will take as parameters the sparse table, ST, the left boundary and the right boundary. First, compute the length, the number of cells or the number of elements in that range. Compute K, which is the greatest power of 2 that it could be included in the sum of powers of 2. And compute the position, the starting position from the second range to have 2 power K elements, and compute the minimum between in the sparse table between STLK and STPK. A single query is constant time, as you see, is the big O1. This is the sparse table efficiency. It's n log n time over pre-processing. It will take for one single query. For single query, it's the constant time, as you see. And the extra space complexity is the sparse table itself is n log n, because we have n row and log n plus 1 column. We can say log n. Now let's code our problem, the same problem here. Let's see it first. That will we're going to use the sparse table to solve this problem. Given an array of n integers, your task is to process q queries of the form what is the minimum of the value range AB. The first input is to NIQ, etc. The second line is the number of the elements or the integers in the array, and the output will be the result of the range AB, as we have an example. So we're going to solve this problem using the sparse table. As we have seen, the time complexity of a single query is constant time. The time complexity of the total RMQs is the OQ, where Q is the number of queries here. The time complexity of the whole code is L log n plus OQ. The space complexity is the linear time of the original array, and the n log n for the sparse array. First, we're going to read the inputs. Now, let's build the sparse array. First, I will compute the size of the sparse table, and let's make a function, call it build, that will take as parameter n a, the original array, and the n, or the size of the original array, and let's take st as a result. Here, call it st as parameter, and declare st is long than array is a matrix here. Matrix st is equal. Let's allocate the memory. And this is the number of rows, and allocate the memory for the columns. St of I is new long n. Okay, let's implement the function build. It will take as parameter the array, the original array A, the size of the original array, and as a result, we're going to have the sparse table as a result. Okay. First, we're going to use the dynamic approach, as dynamic programming approach, as we have seen. First, we're going to fill the first column by the elements of the original array, and using dynamic programming, both the bottom up technique or approach, to fill the other columns. We're going to fill the column by column. So we're going to fill to the next. We're going to fill the next column. 2 power j. It must be 2 power j must be less or equal of n, as we have seen in the slides. And we're going to fill the rows. We have to be careful that the position, which is in I plus 2 power j, 2 power j minus 1, must be less than n. The position of the, if we take 2 power j elements. So st of I j, as we have seen, is the minimum. The minimum at, we're going to use the previous columns, first starting from I, and the position of the next 2 power j elements, which is from I plus 2 power j, I think minus 1 here, if I don't forget, j minus 1. Okay, this is how to build the sparse table. Let's verify all the computation here. I don't know where is it, as we have seen. And first here, this position P is, we can compute the position P of the starter from I. If we take 2 power j element, what's the position P? The position P is I plus 2 power j minus 1. So that's it, what's the position here? I plus 2 power j minus 1. So this one must be less than n, from 0 to n. And when we query, what's the position of the starting position of the next 2 power j elements, second range. If we query here, I think this one, as we have seen, the two power k's, the two first, not the query here, we're still unbuilding, sorry. Here, here, okay. We're going to use the previous column to compute the current column. So using this formula, that leads us to this one, as you have seen. Well, that position is equal to, we can divide 2 power j cells to 2 power j cells plus another 2 power j cells. So we know that the first position here, which is I, this is the row of the green one here, and the column is j minus 1. But the position of the second here, which is the position, which is, we can compute it. We have seen if we take this position k plus 1, we can compute that k plus 1 is I plus 2 power j minus 1. So 2 power j minus 1 here, which is correct. Okay, yes. Now let's query RMQ. It will take the sparse table, the left boundary, and the right boundary. First, we have to compute the length of the number of cells in that range, which is R minus L plus 1. Then we're going to compute the greatest power of 2 included in the sum of power of 2's of that length of the range from left to right. And we're going to compute the position P. What's the position? Is this one now on the querying this one. So as we have seen that the range from left to right, it could be divided into two ranges. The first one is starting from A and takes 2 power k elements, and the second range is starting from position P. How to compute that P? We know because R minus P plus 1 is equal also to 2k elements. No matter that the two ranges overlap here, because the minimum is a idempotent function. So that position is R plus 1 minus 2 power k. R plus 1 minus 2 power k. And that function will return the minimum between these two ranges. The minimum of the first range and the minimum in the second range. LK and ST PK. Okay. Let's come back here. This is how to build now querying. Let's display the result. Is RMQ range minimum query. We're going to use that ST table that we have just built, and the left boundary -1, because in the problem the left and the right boundary are one based index. And finally we go and delete the sparse table, the pointers. Let's take the first test. Try it. Okay, we have a problem here. We have 9. Why 9 here? sorry, because here we have to reduce L and R before doing the RMQ. That must be a prefix operation here. I think this is the mistake. Yes, so let's test all the cases here. Okay, failed here. Okay, because I didn't make a carriage return here. Okay, let's try to submit it. Sparse tables, sparse table, submit. Okay, as you see here, all the tests are passed. So the sparse table is a good approach to resolve a range minimum or maximum, or a range query in general. But a condition here, the function must be idempotent, as we have seen on the slides. The time complexity of the single query is constant time, as you see, is very good. But here the pre-processing is O n log n for the pre-processing. So the whole time we can say that is O n log n. I will give you two problems to practice using the sparse table. Of course, we can use another logic or another approaches to resolve these two problems, but here we're going to use the sparse table to solve these two problems. The first one is the problem 239 slide and window maximum from lead code. This one. And the second one, the problem C from code forces, 5C from code forces, longest regular bracket sequence, this one. I hope guys that you will give a try to practice these two problems. I hope also that this part is very helpful for you. Thank you for watching.